So from spin glasses to large language models, before I start, I would like to acknowledge the people that really did the work. The main people are Sue Penn, postdoc at Harvard, Eli Hahami, college students at Harvard, and Hak Stepanians, physics graduate student at Harvard. Sue and Hak are here, so you can ask them more questions. Zaychen, Roy, Zvi, and Dan Lee also collaborate, and the acknowledgement of support from ONR, Amazon, Kempner, and Gatsby. Okay, so what I am going to describe is kind of an ongoing project aiming to explain or to build models and to understand how agents, humans, animals, form lifelong episodic memory. This is basic cognitive function performed by brains of intelligent animals, but it's challenging both from the perspective of explaining this property, this behavior from theoretical neuroscience, and also achieving this behavior in AI. Okay, so let me start from the origins. As most of you know, actually the problem of memory in neural networks was the problem that was an entry point for many of us from physics to transitioning to neuroscience and neural computation in general. Okay, so the Hopfield model of associative memory, you all know, a recurrent, shallow recurrent neural network, and the memory is encoded by a simple Hebb rule, where at each time there is a new experience, the new pattern is coming into the network, then there is a Hebb rule update of the connections. So this, under suitable conditions, generates a landscape of multiple fixed points. Ideally, each fixed point is a stable fixed point, correspond to one of the memorized patterns, and they have nice basins of attraction. So that's kind of the idea. So memory encoding is lasting changes in synaptic connections, hopefully make the memory states attractors, fixed point attractors of the network. And the model also explains what memory retrieval means. Retrieval means that you start with some cue, within the basin of attraction, you converge to the nearby memory state. Okay, so what can we say about this model? So many of you may also know the capacity calculation for this model. Again, the first or one of the first statistical mechanics a solution of an interesting neural network behavior. The accuracy of retrieval of memories is a function of the number of patterns, which you can think about it as a number of patterns per neuron. So P will be denoting the number of patterns encoded into the system, and N is the number of neurons or number of connections per neuron in this recurrent neural network. So as a function of this parameter alpha, memory is retrieved almost perfectly up to the capacity, which is in this case around 0.14, and then beyond this, the memory is essentially collapsing. So all memories are essentially erased. So that's the first, a very dramatic example of catastrophic forgetting. Actually, there are good side and bad side. The good side is that if you are below capacity, you almost have a almost perfect retrieval of memory, no forgetting. On the other hand, if you are above it, you don't have a graceful forgetting, but actually catastrophic. So that's one issue, which I'll come back to it again and again later on. Another important issue is that the Hopfield model is nice below capacity. Capacity is extensive in the number of neurons. However, it is highly sensitive to correlation. So basically, for binary random patterns, it's a very good model. But if the patterns are not binary, the patterns are correlated, it's a very poor model. There are other more sophisticated RNN models to deal to some extent with correlations, but this model typically employ a batch learning. It's not an online or continual learning. So continual learning requires more or less something like a Hebb rule for this problem, and this doesn't work. All right, so this has been a longer-term problem. For 40 years, we have been actually struggling with this problem, how to make neural network models learn, memorize realistic memories rather than random binary patterns. So particularly, we're talking about human episodic memory. They are not patterns, they are narratives. You can think about it as sequences. They are rich with semantic structure. Memories interact with existing semantic knowledge, so it's not a standalone system. It actually each memory is a pointer to an object that is known, or concept that is known already by the system. So there's a close interaction between the memory system and the semantics knowledge. It also integrates into semantic memory. It enriches semantic memory. Fundamentally, it's acquired sequentially, which means that there's a potential interference between memories. Old memories may be erased due to incoming memories, and potential interference with base skills or base knowledge of the system. And finally, it's crucial to understand it if you want to understand not only memory per se, but also understand personhood. What does it mean for somebody to be I? There are certain key elements, but memories, or autobiographic memories, is a very essential element in that. So understanding episodic memory is crucial to understand the emergence of a personality or personhood. All right, so now we have large language models, so it's time to revisit the problem, and that's what I'm going to discuss today, the sequential storage of episodic memory in large language models as a potential models of how human brains, or maybe brains of other animals, store sequentially episodic memories. All right, so I'll talk about two parts. The first part of my talk will be about continuous storage of episodic memories in what we call MEGA, which is gated low-rank adapters in LLMs. I'll explain it. This is work done primarily by Sue and Eli. And the second part, there will not be statistical mechanics here. This will be overview of our empirical effort largely. And then I'll talk about statistical mechanics, zoom in about storing a single episodic memory in low-rank weights, and that's a work by Huck. All right, so first of all, how do we study episodic memory in large language models? Episodic memory is primarily autobiographic memory. So what data we use to simulate and to explore this? We need data. You can take maybe from some novels, some autobiographic diaries and so on. What we have chosen to do is actually to build large-scale autobiographic database, so fictional character, realization, and basically it's like a diary that this fictional character has been writing for himself over the span of 50 years, kind of chronologically ordered. We have a lot of effort in generating enough diversity and realism, and et cetera, et cetera. It's still an ongoing project, but we are happy. I think it's a very good database. We have about 1,000 of such stories. Examples are here. On a hot and humid day in 1966, my family took the subway to Coney Island. I ate my first hot dog, rode the wheel with my father. And then at the end, typically we have something which has to do with emotional valence, because this part of what episodic memory is. So in this case, the smell of salt water, popcorn, etc., created a powerful sensory memory for me. Now, 12 years later, on a day in late August 1978, my parents and I loaded our car with 2 suitcases. I went to Colombia, and again, I felt that this is marking the official start of my independence, and so on and so forth. So every episodic memory is a story of roughly this length about a memorable episode. There are about 20 of these every year, spanning 50 years, so it's about 1,000 stories like that, okay? So that's for all of you to use, okay? to study principles of intelligence. All right, okay, so this is what we call episodic memory. As a control is something which is more conventional in knowledge injection in LLM studies is Wikipedia dataset. So these datasets are datasets that the particular LLM that we are studying have not seen. So this is post-dated of the release of those language models. And this is a typical wiki dataset. It is also, you can think about episodic, it's a factual memory. And very often when people talk about episodic memory, they don't make distinction between this and that. But if you look more closely at cognitive science definition of episodic memory, they really mean something which is personal, experiential, versus something which is facts about the world. Okay, not always the distinction is clear, but that's okay. From our purposes, as you will see so far, there is the story, the behavior is more or less similar with subtle difference between them. But on the long-term horizon, we want to focus on this to understand agent, personhood, and so on, because this is crucial for them. All right. Okay, so that's the data. So what does it mean to have memory in language models? So you all know there are several conventional ways to do it. Context window is one way. You store information by putting stuff into the context window. From the perspective of cognitive neuroscience, I would say a context window is kind of a short-term memory or working memory. Another type of memory is RAG. You all know that. And again, from the perspective of understanding the brain, we don't have in the brain any disk to use. What we really focus is on fine-tuning. So continual learning of continuous sequential memorization by fine-tuning. That's our goal, to understand how you take language model, pre-trained language model, and fine-tune it sequentially to encode those memories. And this is, the limitations are crucial. The limitations, first of all, as I said, you can previously fine-tuned knowledge of previous memories can be overwritten, and also base model can, base properties of the LLM can be also degraded. So this has a very, at least one aspect of the challenge is the aspect of continual learning. Continual learning is a big challenge in deep learning, AI, in neuroscience. It's a broader question about learning sequentially tasks, and there are a lot of literature about that and studies, and we have published recently a paper on that, which you might want to read. And this is particular instantiation of that, where the task is simply memorizing a single episode. All right, so how do we overcome catastrophic forgetting? So there are in the literature, there are many approaches. One approach is regularization, what I mean specifically weight regularization. One way or another, you try to limit the change in the weights when you learn task 1 or task 2 relative to the weights previously. There are various ways of regularization. Another one is architectural. You somehow separate things, not to make them interfere with each other. And finally, the last one is replay, which says, well, you refresh. So in some sense, you go to a batch mode rather than to continual learning mode. All right. All of them have some analogy with probably with the brain, and I'll talk about it. So I'll talk about all the first two. The last one, we have done a tremendous amount of ongoing work on that, but I won't have time to talk about. Okay, so here is the example. So by the way, all our simulations are in Llama 3, 8 billion instruct. And this is the way, if we just, there is, of course, the question of which layers, and you do fine-tuning or you do low-rank adaptation, and there are many hyperparameters. I won't go into that. I just say that universally what we find is that there is a strong forgetting. So on the x-axis is the number of stories that are entered into the system one by one. On the right axis, on the y-axis is the accuracy, and as you can see, there is a very strong forgetting. So the recall accuracy of the first story, after learning 10 or 2 or 100 and so on, there is a very strong forgetting. Again, depending on the parameters, maybe slower, maybe faster, but in general, it is problematic. What about the property of, what about regularization? So this without regularization, one very popular and effective regularization sometimes is L2 regularizer, restricting the change in the weight, the L2 of the weights from one instant to another. We tried that. As you can see here, it doesn't really improve. If the regularization coefficient is too small, it doesn't do anything. If it's too strong, you don't memorize. Similarly, a more sophisticated regularization, which is called elastic weight consolidation. Also, we tried that. It doesn't seem to work very well. So our conclusion is that regularization for this task is not helpful. Okay, so what can you do to resolve this problem? Okay, what about the base model, base knowledge? So on the left-hand side, again, it's the same type of forgetting. This is for wiki, this is for the character. Both of them, the character may be slightly faster, but it doesn't matter. It's interesting, the base knowledge, popular measures is PPL and MMLU. Large PPL is bad, small MMLU is bad. Here it looks like that depending on how extensive the fine-tuning is. If the fine-tuning, the blue curves is the fine-tuning is all the parameters in the network, then there is a modest effect on the base knowledge. If the fine-tuning is done on 4-layer, rank 4, and so on, then there is a very strong effect also on the base knowledge. All right. Okay, so what do we do? So briefly, what our solution is to store memories in gated low-rank adapters of LLM. I explained what it is, shortcut mega. There is an old preprint in the archive, very outdated, but I'll give you basically the highlights. So we're building a model which is kind of inspired by the hippocampal cortex separation or dual role in memory. So according to this, fast encoding of memory traces are by cortex hippocampal pathways. Importantly, we are using the notion of, or we are building on the notion of memory engrams. It is, there is an empirical evidence in neuroscience for some memories that are stored separately in separate populations. It is controversial in neuroscience, but we're adopting this approach, which means that traces of separate events are protected through a competitive network, so they don't interfere. So that's our solution. The recall is using gating units that compare stored events, summaries with incoming cues, as I'll show. And then consolidation is by a slow transition from the hippocampus to cortex via slow fine-tuning and rehearsal and so on. All right, so here's the diagram. So we think about the base LLM, we think about it as cortex, as working memory, semantic knowledge, and so on and so forth. But now we want to encode memory, so we add, you can think about it as adding neurons and weights to model hippocampus fast encoding of hippocampal episodic memory. So this is kind of low rank 1. So you have input, which are connection from cortex to hippocampus. You have nodes here which are denoting the activity of the low rank units, and then from them up projection back to cortex. And this is the way, this simply low rank adapters of memory 1. But now at the same time that we store this memory, we also store an embedding of the entire story, like a summary embedding in units, which are the gating units. Now, memory 2, you do it again, but separate units, separate LoRa, memory 3, separate LoRa, etc. And the gating units are acting as winner take all to select the relevant memory. So for instance, you encode memory 1 again by this low rank units. You encode in the weights of the competitive units the summary embedding. You during memory 2 the same. You encode in a separate LoRa the memory 2. You encode in another gating unit the embedding, the summary embedding of the second episode, etc., etc. And now when you recall, you come with a queue, sensory queue, into the context window, propagates through the network, generates an embedding of the recalling queue. That embedding is now compared to the embedding stored in the gating units, and this competitive network chooses the relevant gate, the relevant LoRa to open, in this case, gate 1 and suppresses the rest. So it's a brute force control of which memory traces should be activated at which recalling episode, and this is by this way we are enforcing, or we are preventing interference and forgetting. So you can think about it as basically each pathway is storing one memory, and it's not overlapping with other memories. So that's the model. It's a brute force way to get rid of the problem of interference. You can also think about, if you want, you can think about it also as an additional gating that chooses whether to actually use any of the memories or use the base model in such a way you don't even have any interference between the memory traces and the base knowledge. That's another gating that can be used. All right. So briefly, again, there are many results and details and hyperparameters. I won't go into it, but briefly, it works. So here is an example of this is kind of recall accuracy as a function of memories up to 1,000 episodes. It's almost perfect. This is for wiki. The character has slight decay. Again, there are options, but it's very weak and works very nicely. MMLU accuracy is perfect. So basically, this is the basis of what we are building for the entire system. We are testing performances on QA. We're testing how to move memories slowly into the base model, and so on and so forth. But I'll skip this. All right. So catastrophic forgetting in distributed fine-tuning of LLM. Is even with weight regularization. Mega is embedding-based gating of memories in separate fine-tuned LoRa. And however, there is one of the issues which are important is because each memory basically creates another set of parameters, fine-tuned parameters, they're not overlaying on each other, then there is a problem of parameters. Eventually, you will have too many parameters in your brain, or you need too many synapses. So the budget is very important here. This is why it's important to do it in a low rank and minimal number of layers, perhaps even one layer. You can do the whole thing with just fine-tune one layer of the LLM with a very small rank, and just in this case it's very efficient, so you can add thousands, even 10,000 episodic memory in this way without worrying about getting too many synapses that you don't have.
But if we think about the...
Yeah, sure, go ahead. There was a question? Yes.
Who is the judge of if you recall a memory or not?
Can you say it again?
What is the process of who is the judge if you recall the right memory or not? Is it the question, or do you need to...
Well, I mean, this is a whole long story which I won't get into it, but here it is, you can have, LLM judge, you can have all kinds of more quantitative measures. It works fine in this case. In other cases, we have, when you have continuous, when you have non-gated decay, it's more with a partial recall. You can ask whether it's good enough or bad enough. I won't go into it. This is works whatever judge you use here, whatever measure you use here. Yeah.
I just wanted to ask about, in the brain, the memories are represented by the same set of neurons in the hippocampus.
No, not in our model. No, this is not rat in an environment.
Not in the model, but I wonder if
in our model, in your brain, it's not. That's our proposition. It's
in the brain too. These
in the brain, in your brain, it is gated. It's a memory engrams. Yes.
With separate subsets of neurons.
Yes.
I see.
That's the model. All right. Okay, so now I want to get to the second part, and basically we are back into the question of a single memory, because once you gate, when you have 1,000 memories, basically it's like each memory at a time. You recall one story, you suppress all the rest. So now the question is, can we say something more theoretically about how you store just one episode, one story that I showed, in a single layer, in low rank weights? What type of representation? What can we say about the capacity and other properties of this process? All right. So okay. So here's we are looking at. So this is the details. So talking about the top layer of LLM. The top layers look like that. There is an input layer with size n0. There is an input. So now, okay. There is an input embedding of the token. Everything is of course contextualized. So we're having a story, and now I'm looking token by token this story. So this C, which I'm writing here, is of course contextualized, but still it's embedding of one token with size n0. Then there is a layer mapping it to another layer, which is a feature layer, if you want, the size n. So this is what I call W0. 0 is because it is the base model. And then there is an array of weights, which I call A, which are connecting the feature layer to each one of the readout units. Okay, and the readout units have logit y1, y2, and so on, ym. This is the size of the vocabulary. This is, I don't know, 100,000, 300,000 units in modern LLM. And then there is basically a hard marks choice of what should be the next token. So this is simple kind of next token prediction. You come with a token and you make a decision what should be the next token. So this is what we're going to use, this architecture. We are going to do fine-tuning on this. Yes?
Is the input dimension not the same as the vocabulary? Like, do we think about
Not at all, not at all.
But usually you'd have vocabulary at both ends, right?
No, it's not. It's not the size of the vocabulary at all. Neither n0 nor n, nothing to do with the vocabulary size.
Right, because this is the last layer, what you're showing.
Yes, okay, yeah. I mean, from the theoretical perspective, we can see what is the effect of m. So m is the size of the vocabulary. P, as I said before, is the size of the is the length of a story. So just one story, one long story has p tokens. Okay, a sequence of p tokens. This will be p. There are two sizes, one is n0, the input, and one is n. And then there is m, which is the size of the vocabulary logit, and then there is argmax on that, okay? And please stop me if something is unclear, because all these details will be important. Now we're talking about StatMac, okay? So we have to be, I want to make sure that you don't lose me, okay? So this is just an architecture that's not ours. This is what, you look at Llama and other models, this will be the last layers. The feature layer, the feature nodes here are linear. So from n0 to the argmax of the logit, it's linear. Okay, that's what we're going to do. All right, so this is the base model, and now we want to store memory. So we do it with a low rank adapter. So what? Oh, here it is. So overlaid on the base model, we add now low rank. In this case, is rank 2. So denoted by the following. So there is a a down projection from n0 to r in general. R is the rank, in this case it's 2, so n0 to 2, this is V, and then there is up projection from the low rank units, it's linear units, x1 and x2, to the feature layer, I denote by U. And then as before, A is frozen, we don't touch A, we only fine tune those U and V. The down projection to the rank and the up projection back to N. All right, so that's what we do, that's what we fine tune. Okay, good. So, so memory is stored in this W, this is V times U transpose. But you can already see here something very important, and this is that basically the low rank is a very strong compression of each one of the tokens. It takes a token of size n0 and compresses it to size 2 or 4 depending on the rank. And we'll talk about typically about low rank. Okay, as you will see in a moment, let's say in rank 2, it's not even 2-dimension. It is it can be even normalized to a unit on a circle or an R sphere, and I'll talk about it in a minute. So it's a very strong compression, and that limits what the system, how you store the memory and the properties of the system. All right, so let's get more details. So what is the task? So you come with the tokens, 1 to P, a sequence of tokens. And now, what does it mean to memorize? It means that after you do fine-tuning, you come with token 1, and token 1 is correct. If you fine-tune U and V, token 1 is correctly pointing or choosing Y1, which is the next token, and so on. Token P choosing YP, which is the, I don't know, N token. So these are target layers. So for each story, we take all the logits, all the readouts corresponding to the target value of token 1 to token P, and we order them. So this is Y1 to YP, okay? And then the rest of them, for a given story, do not participate in the sense that they don't have to, they are not chosen for in this story. So this is what we call distractor layer. So this is YP plus 1 to YM. This is a very long, very wide layer of distractors. P typically will be a few hundred or maybe 1,000. The distractor layers in realistic problems is many thousands. But anyway, that's a structure for this. Okay, so that's the task. So fine tune U and V means that I have to correctly do the mapping from each token to the target, and the target means pointing to the next token. Now, of course, pointing to the next token means that it goes into the logits, it chooses the next token going through the entire network and generates the correct contextualized token 2, and so on and so forth. So all these token representations are contextualized, but the contextualization is done by the system. We don't touch it. We only touch the last layer, so we don't have to worry about messing up with the contextual representation. All right, so let me first talk about ignoring the base model. Think about fine-tuning V and U to very large values so that their input to the logic is completely overriding every input coming from the base model. This is clean and simple, and let's see what we can do about that. Okay. So here's the main issue, the main insight is the following. So if I go back to here, okay, so first of all, in this case, let's say R equals 2. In this case, each input token is represented by a point in 2 dimensions, but because of the argmax, the magnitude of this doesn't matter because it doesn't change the decision. So we can actually normalize to unit vector. So each token is mapped into unit vector on a circle for R equals 2, and an R sphere, it will be general a point on the sphere. So this is the encoding of the memories. And then eventually, and then each point here, each node here is connected to each one of the readout units by a functional connection, which is a single functional connection going from x1 to y1, from x1 to y2, and so on, and similarly for x2. So this layer has functional connection of 2 dimensions to each one of the readouts. Okay? And then the actual logic input to each one of the readout is the dot product between x and this functional connection. Okay, so I'll denote the functional connection by Hn. N is one of the logics from 1 to m. It is a dot product between the frozen A, I'm not touching A, and the fine-tuned U. Okay, so for each one of them there is a number. So I have all these connections. So H is a 2-dimensional or r-dimensional functional connection from the low rank representation to each one of the logics. Okay. So the actual input, as I said, is a dot product between them. All right. And so what is the constraint? What does it mean to solve the problem? So let me first say the following. We can forget about V, because what we have to worry is about what X should be and what U should be to determine the logics. V will just do a linear regression to map between the input embedding to the desired low rank embedding representation. So that will be taken care of by regression. So all that we have to worry about 2 questions: what should be the representation on the unit sphere of the tokens, and what should be the use to make sure that they map correctly. All right. So this is the inequalities which have to be obeyed. That the functional connection of the target, which is for input mu, the target is h mu, y mu. So this would be bigger than all other inputs, right? So that's the winner take all. So that's what the up projection have to do. Up projection have to be fine-tuned to obey all these set of inequalities. All right. Okay. So okay. So but there is additional symmetry, which are interested in the problem, and this is one can show very easily that there is not much choice for the h mu but to be aligned with x mu. Because if they're not aligned, then by symmetry, because you have many axes on the sphere or on the circle, then the h mu cannot match this. This inequality. If you think about nu, which is close to mu, and you think about the symmetry conditions, the continuity, this actually very easy to show that this has to be the case. So this means that we have a unit circle where the low rank representation embedding of all the stories lie on, and on the same unit circle or the same unit sphere, all the functional connections also lie on. And so the U's have to obey this equality, P equalities, and at the same time they have to obey for the distractors the inequality that it should be less than 1. So this is the set of the StatMech problem. You have to choose the U's such that the target functional connections align with the representation of the corresponding input, and the distractors are all losing because they are less than 1. All right, so let's talk about the scales. So we have several scales. We have n goes to infinity, p goes to infinity. We have alpha, which is the number of tokens, the length of the sequence divided by n. N is the feature layer representation before the logics. Beta is the scaled size of the entire vocabulary. So m divided by n, and again this should be finite, alpha should be finite, beta is naturally big or equal to alpha, and we assume that the frozen readout weights are Gaussian. Okay, so now we can define the capacity as basically the maximum alpha given beta or the maximum beta given alpha for which all these constraints are obeyed. So it's well-defined set of constraints and to solve by StatMech. Okay, Now, there are two options. One option is to fix x mu, to assume that they are randomly but uniformly spread, uniformly overlaid on a regular lattice on the circle or on the unit sphere in general, and only study the mapping from x to y by u. This is what we call fixed x mu, and the other one is a more sophisticated training where we actually train to find the optimal way where to put each one of the memories on the circle, in addition to training to find the appropriate weights h mu. All right.
You said that
Yeah.
you're still having linear features.
Yeah.
But why? Because if you're only training the low rank part, you have like a finite number of vectors. Can't you also have nonlinearity for the feature?
Where do you have nonlinearity?
Like, why can't you have nonlinearity at the feature layer if you're only?
But we don't have nonlinearity.
Why not?
LLM doesn't have nonlinearity.
It's a choice.
That's the base model. We just fine tune.
Because in
W.
principle you could write down.
That's what we do. Yeah. That's the architecture of the network. Okay. All right. So you can do. So first of all, is this story correct? With all the story that I'm telling you that h mu will be aligned with x r mu, is it correct? Or is it just physics hallucination? So here is a simulation of the problem. So here it's just on what you see here on the right-hand side is no assumption that take the model and simulate it for r equals 2, and you see the x's are all, both the x's and the h's, the target are all on the unit circle, and then all the distractors, all the functional connection to distractors are within it to obey the inequality. And this is, you can think about it, is basically when a memory enters into the system, it generates a cosine profile of inputs to the target layer, and this is what's shown here. And basically it is like a bump attractor, if you want. You basically, by the winner-take-all nonlinearity, you choose the one with the top. So this is the correct decision. All the distractors are lower than 1, and therefore they correctly do not win. So it's a very simple, nice architecture, and really connects to notions of attractor manifolds. In recurrent neural networks, here the recurrent neural network is simply represented by the nonlinearity, which is the winner-take-all nonlinearity, which is basically an extreme case. You have a bump attractor, you choose the one which is on at the largest value in the center. One difference between a bump attractor in a recurrent, typical recurrent neural network is that there are no distractors, so you don't have this. You just have the cosine profile of inputs. But this cosine profile of inputs in our case is spanning the target layer, but then there are many distractors, and they have to be suppressed, so this extra constraint on the system to be solved. Okay, so this proves that our symmetry and continuity assumptions are really valid. And now we can do the good old replica calculation, the StatMech, Gardner, volume, and so on, and then try to find the capacity. So first of all, we can do without much calculation, ask what is if beta equals to alpha, no distractors, what is the maximum alpha that can be? And that's very easy to convince you that it's alpha equals to 1. And the reason why it's 1 is because you have you have here p times r. This is equality constraint. You have p times r in equality constraints. Okay, and that's and you have n times r weights. Low rank weights, so then alpha must be 1, independent of R. So the maximal capacity in terms of alpha is 1 for all R. Even if you add rank, you don't change that. But R does affect what happens when you have distractors. So when beta minus alpha is bigger than 0, as you can see here, there is a suppression of the capacity because of the constraint imposed by the distractors. But here R is effective. This is for R equals 1. It doesn't matter here. R equals 2, 3, and 4, and so on. So there is a very substantial improvement in capacity when R is large, but not at the maximal value 1. All right, and actually for small alpha, for large beta, the same curve, you can show that there is a logarithmic cost for having distractors. So it's a mild cost, so beta is exponential with R over 2 alpha. So for instance, for R equals 2 and beta equals 30, which is a realistic number, alpha is 0.2. The suppression is mild because of the logarithmic relation. All right, so, but there is a problem. The problem is the margin. So again, because you have this cosine tuning, then the winner is at the center, but then the next one to the winner, in the winner take all, the next one is very close to it because of continuity. So basically you have cosine of theta minus theta 0. Theta 0 is the winner, but the next one is close to it. So if you think about the margin is kind of the scale difference between the winning logic and the next one. It is small. It is basically, in terms of the angle, in this case, it's 2 pi over p. In terms of field, it's the square of that. But anyway, it's the larger the p is, the more dense the distribution of those inputs on the both the inputs and the functional connections on the circle, on our sphere. So you have as p increases, margin goes down. When you increase R, then you separate them into higher dimensions, so it's slightly better. Here P is 1 over R minus 1, but still for low R, it's, so here you can see for difference. So this is an important constraint, that if you just use this naive model and you, by the low rank nature of the process, you are paying the price of a low margin, which is less of a lack of robustness. All right, so now what happens if we train X? Now we can say, okay, if you train X, maybe the system has a nice way of separating them in such a way that everything will be fine. You can do that, you can try that, so you can solve the StatMech with training X. So now we are training X and we're training H. So we don't impose, it's still on the circle, but we don't impose the location on the circle. It turns out that in this case, so the previous case, when X is fixed and all you train is the U, in this case it's convex problem, replica symmetric is fine, and is completely agreeing with the simulations. If you assume that if you train both X and U, this product is a problem, is non-convex, and you need replica symmetry breaking. So you can see here, again, this is beta minus alpha. This is alpha equal to 0. First of all, you can, by the same symmetry argument or counting argument, you can show that if you train X without doing any calculation, alpha max should be R. And the reason why is because once you train X, you don't have R constraint, because you don't constrain the angle, you only constrain the magnitude. So you have one constraint per R. So you have only P constraints and you have N R weights. So the capacity when there are no distractors is exactly R. You don't need to do any calculation on that. Okay? So now let's see what the replica symmetric solution does for I equals 2. This is this line and definitely wrong. So replica symmetric is the wrong solution in a very bad way. Okay? So this is a simple, cute problem, and you'd imagine, well, you know, approximately correct. It's not even approximately correct. Okay, if you do one-step replica symmetry breaking, so I'm sorry, but by the way, this is the replica symmetric solution for fixed R, which we saw before. It starts with 1, as it should start with 1 for any R, and that's what we saw before. So now this line here is the solution of one-step replica symmetry breaking. So as you see, it really starts with R, and this is R equals 2, so that's good. And then kind of steeply increases when beta minus alpha is bigger than 0. And these are the simulations for train X, the points here. So there is still a discrepancy. We don't know whether the discrepancy is coming because the simulations is finite size, or the discrepancy is coming because we didn't have a good, very accurate solution of the one-step replica symmetry breaking, or whether likely one step of replica symmetry breaking is not enough. But it's definitely doing much better than the replica symmetric, and as I said, it starts in the right place and kind of grows exponentially as we expect. All right, so this is trained X. So the capacity, the maximal capacity is improving, is scaling as R, which is good, and then the whole curve is, of course, the capacity is larger. However, now you can ask, okay, what happens where all this, when we train X, where all these units are, where all these points are? It turns out they are random. And actually, the margin is even worse, because when I fix X, I can put them regularly on the lattice. But when I train X, the system just, what it does, it just uses them random, just Poisson. So you can see that the margin is actually arbitrarily small, 0, like if you randomly distribute points on a circle rather than on a lattice. So from capacity is larger, from the perspective of margin, it's actually worse than fixed. So first of all, it's two things. First of all, the capacity is larger. However, the problem is not convex, so it's hard to actually solve the problem, not only theoretically, but also by simulations. And secondly, the system is less robust because of the margin, small margin. All right, now to close this one, what is the memory efficiency counting? And again, here it's important because this is one story. Every story you will have the same number of weights added, but it's very nice that you can actually completely solve it. You can show that the number of weights parameters per token is given by this formula. Now, what should be taken for alpha? It depends what we choose. We can fix the size of the vocabulary, makes sense, and vary the embedding n to maximize the efficiency. In this case, n should be as large as m, and basically n equals to r if the fixed r x and trained x is r plus 1. So it's order r in both cases, but this is slightly better when train x. Now you can also say, well, n is fixed by the hardware, by the brain, by the LLM, so both m and n are fixed. This generates beta, which is large, like 30 and so on. In this case, n is slightly larger, is r plus 2 log beta, but not so bad. Okay, so that's the conclusion of this nice part. But we are still struggling with the question of how to generate a better model that will not suffer from this very small, either 0 margin or very small margin like 1 over p, 1 over p to some power. Okay, so now the idea is let's go back to the model and add the base model. And the notion is the base model should help, because this is a read story. The tokens are contextualized, and the task is to really generate the next token and so on and so forth. So the base model knows a lot about it, and should help without even fine-tuning. Should make the problem easier. And indeed, you can just do the simulation. R equals 2. This is for trained X. So remember, for trained X for R equals 2, without the base model, the capacity should start with 2, and then the capacity should be 0 above 2. And you can see here that with the base model, the capacity is increasing, is close to 5 for depending on beta, of course. So in this case, beta equals to alpha. As you can see here, the capacity is close to 5. But more importantly, the margin is order 1. Okay, so this is just simulation. So what you see here is that that adding the base model although the representation is still the same, you map input into 2-dimension and so on and so forth, but adding the base model contribution increases the capacity, but more importantly also generates a comfortable margin. All right, so we want to understand that. So first of all, here's what's going on. You can understand what the base model does. You have W0 for each input token. W0 gets a contribution, and this generate contribution, and this contribution is generating a net bias. So B mu is the bias from the base model, the input from the base model for token 1 on its correct target, and B mu n is the base model contribution of input to the logic n, which is in general not mu, so this will be the wrong, this is the bias to the wrong guy. And the question is with delta B is, what is the structure of delta B? So you can see here an empirical histograms. So this is delta B mu, it's the relative bias. So positive is good. Positive means that the target gets more input from the base model than the non-target. This is for the distractors, and this is for the target layer. Okay, so, but as you can see, the vast majority of this relative bias is positive, which means that the network, the base model, knows that, for instance, that if I say I met my friend, it's unlikely to be that the next token will be some mathematical equation, okay? So the base model definitely helps. However, this is somewhat misleading because the tail is very important, the negative tail. Because if you are, because to make a correct next token prediction, you want that for each input, there will not be any non-target with a larger bias. So this means that for each input, many of the potential target or distractors are suppressed by the base model already. But you cannot say, okay, let's forget about the fine-tuning. The base model does the job. No, the base model doesn't do the job, because for a large fraction of each of the tokens, there are a few negative. The model cannot predict correctly the next token. So that's kind of the structure. So the question is how to incorporate this into a model. This is statistical, mechanically speaking, is a hard problem to kind of fully capture it. But what we have now is kind of a toy model which captures the essence of it. The toy model says the following. For each token mu, this net bias is constant, is delta. So basically we say all tokens have this kind of background positive bias. Okay, so now the constraint now is that, I'm sorry, this should be plus, I'm sorry, this is a mistake. So now the constraint is that the fine-tuned LoRa contribution from a comparison of the target and the non-target plus the base model contribution should be bigger than kappa. So that's the inequality constraint. However, we have to, as I said, we cannot just say, well, everything is positive, because then you don't need the model. You can take H to 0 and the base model do the job, which is of course incorrect. So we add a constraint that the functional connection cannot be too small. They have to be bigger than some kappa 0 in order to effectively ensure that they take care of the few negative biases. Okay. So if you look at this problem and solve it this is for fixed x, okay, and let's say beta equals to alpha, that there are no distractors at all. Here, this is this curve. I'm sorry, I'm losing again mine. Okay, so this curve is for beta equals to alpha, no distractors. And you can see that in this model, with this is r equals 2, this is for fixed x. without the Bayes model, the capacity is never above 1, and here the capacity is larger than 1. As we saw that this is in a real simulation happens, that the Bayes model increases the capacity, so that's consistent with that. And in addition, the kappa is order 1. This is fantastic. Okay, so now you see that even in this toy model, we get the ability to separate between nearby logits, and this is kappa order 1. Okay? So and these different curves is when you have more when you turn on distractors, so beta and beta. So you correspondingly have a lower capacity. So what really happens here is the following, and this is shown here. What happens here that by having the Bayes model contribution, which is largely positive, you are not constraining. So the X's are on the ring, but now the H's are now are free to be lower, to be in magnitude, to be lower. So they fill in an annulus. And the reason why they can be lower is because this lower magnitude of the H's is compensated by the largely positive bias. So instead of having both H and X on the ring, now H are filling an annulus where X is on the ring. So this is what happens here. When alpha is less than 1 in this toy model, you go back to this ring. All right, so that's it's a toy model which captures the essence of the qualitative essence of what happens in the real model with the full-blown distribution of biases. But it does in our mind capture the most important things: increased margin, increased capacity, and increased margin. Okay, so let me summarize this. Ambitious interpretability, maybe the first ambitious interpretability of memory encoding in large language model by statistical mechanics. It is simple, relatively simple, and exact. So we have estimate of the scaling, what is the relevant scaling, beta and alpha, and so on, the capacity, the margin, and the role of large vocabulary. It illuminates the nature of the solution and kind of what is the representation of these tokens in one story. It's connected to ring attractors, as I described. The role of non-convexity, if you learn both the representation, the low-rank representation, and the output connections, it becomes non-convex, and replica symmetry breaking associated with that. And parameter efficiency can be estimated exactly. And in this case, if you look at what contributions are, it's largely determined by the size of down projection weights N0 times R. This is the dominant constraint. Without the Bayes model, the margin is low due to low rank compression, as I showed. With and this is true even if you train X. Actually, it's worse. If you train X, the margin is 0 because it's just distributed randomly rather than on a lattice. And the Bayes model weights generate largely positive biases, not completely positive biases, but largely positive biases. And therefore, this is enough to improve both the margin and the capacity. And finally, open questions about the entire project is the several milestones that we have to achieve, and some of them we are working on now. One of them is, I discussed mostly memory, but even episodic memory stored as an episode. It's something that is not only accessible for reconstruction, it's also accessible for semantic interrogation. Basically QA. If I can ask, okay, where did my last birthday party happen, and so on and so forth. So this turns out to be more challenging because it really have to do with reconstruction and synthesizing knowledge rather than simply reconstruction the sequence. It's also related to the question of Bayesian of attraction. How do we think about Bayesian of attraction? If we have just fixed point memory, like in the good old Hopfield model, We think about Bayesians. You start from some initial state, you convert to a state. If you think about the classical Sompolinsky and Kleinfeld sequence memory in a shallow attractor neural network, the Bayesian of attraction is basically the Bayesian of the first state in this sequence. Okay? Once you reach the first state, you move on. But here, because of the contextual interaction between the tokens, it's more complicated even to define mathematically what Bayesian of attraction means. As I said, eventually you want to move from the LoRa, move memory as a semantic knowledge into the base model. For this, you can think about it as a slow rehearsal of the memories which trigger kind of batch learning on the base parameters. And that's one project that we are working on now. What are the limitations on that? And finally, as I said, our long-term goal is to have enough episodic memory fine-tuned into the brain of an agent and synthesized into its semantic knowledge to show, to test, and to define even in statistical mechanical terms, what does it mean that a personhood is emergent? What are all the parameters? What are the time scales? And so on and so forth. All right, so that's what I had to tell you today. Thank you.
The base models, how do they change if the models get stronger?
If what?
If the models get stronger, if you look like
No, comparing different models, it's a very good question. We have so far we have done almost all of it in that model, but we are exploring now, beginning to explore other models, even more primitive models and more modern models. Where is Sue? So he will tell you more about it, but we're only beginning about that. With that, most of what we have done is, but that's a very important feature to look.
I mean, would you expect the tail to be better, or the biases themselves to be larger in magnitude? Like, what would you?
No, it's not. The overall magnitude is not important. Everything is scaled because you're fine-tuning weights. You can scale them up or down. So it's not about the magnitude. It's about the distribution. And basically, it is given a story. You look at the base model. How much of it is predicted well by the base model? Okay, that will determine. It's not only the model. It's also the kind of data, right? You can imagine if it is a mathematical set of mathematical equations, it will be different than it's just everyday like story. But we are focusing on kind of everyday like story. We are not doing science or math or coding. The goal is to understand how naturalistic events are stored in the brain, and so that's what we are in. Yes.
Do you have any hope to get a more fine-grained understanding of what the base model is doing beyond just inserting biases?
Possibly. As I said, I've shown you distribution, but the distribution, it's a difference between quantities which are themselves, matrices, bi, mu, nu, and so on. I think it would be interesting to understand the structure. Do some low rank something about these bias matrices and so on. We have not done enough of that, but I think this will be very interesting. In general, not necessarily for this, to understand better what the base model does with some new information of that type coming to it. Yes?
If you have used softmax, would that have encouraged the margin to be bigger?
The what?
The margin, would it encourage the margin to be bigger if you use softmax instead of like altmax?
Yeah, but it is correct, but it's how what you define, once you have a stochasticity, maybe it's like temperature, it's interesting direction, but it makes life, which already complicated, even more complicated, because you have to, everything now has to be probabilistic, and what are the measures, one mistake can take the whole thing into wrong. This very, very easily, you make a mistake in a token that the system starts to hallucinate. So you get into all these problems. For instance, but it's related to that. Even with the hard marks, if we look at cases where where the reconstruction is not perfect, okay? Imagine you are above capacity or something like that, right? So then you can ask, what is the nature of the error? Is it, a few tokens here and there? Maybe it reconstructs semantically correct, but not precisely token by token. Already mentioned here about that. So, what is the judge and so on. Is it start to hallucinate, or it start to mixing things between stories? So we have a whole project of trying to analyze the nature of errors when they occur, okay? But this even without having on top of it another noise. But in theory, you're right, that we should have also extending our understanding to the case where there is a softmax rather than hardmax. More comments or questions or suggestions? Yes?
So I may have missed this, but the distractor tokens, are they more like random tokens, or are they non-memories? How do you pick the distractor?
In this, the distractor tokens are basically all the logics which are not supposed to be active during the generation of one story. So there's nothing special about them, because another story will activate another group of P targets. Okay, so it's not something that they are bad or good. For each story, we are looking at all the targets or all the logic that are supposed to be active. Okay, and we call them targets. And the ones that are not supposed to be active in that story are distractors. They are distractors relative to this story. Another story will have another subset of targets versus distractors.
All right.
All right, okay, thank you.
Yeah, thank you very much.